What if we could unfold a map so vast it doesn't just cover continents or oceans, but entire galaxies? Picture this, a cosmic atlas where the edges aren't defined by mountain ranges or coastlines, but by swirling nebulae, rogue planets drifting in the void, and galaxies so distant their light has traveled billions of years just to reach us. This isn't science fiction, it's the thrilling reality of interstellar cartography, a field where scientists are pushing the boundaries of human knowledge to map what lies beyond the Milky Way. And what they're finding is rewriting our understanding of the universe itself. Think about the last time you got lost, maybe in a new city or a dense forest. That moment of disorientation, the scramble to find a landmark, a path, anything familiar. Now imagine that same feeling, but on a cosmic scale. For centuries, we've navigated the stars using constellations as guideposts, but beyond our galaxy, those familiar patterns vanish. The darkness isn't empty, though. It's teeming with wonders we're only beginning to catalog. Black holes spinning at the hearts of distant galaxies, mysterious dark matter weaving invisible webs between stars, and planets so alien they defy imagination. Mapping these realms isn't just about curiosity, it's about uncovering the hidden architecture of the cosmos. So how do you chart the uncharted when the territories you're exploring are light years away, shrouded in darkness, and often invisible to traditional telescopes? The answer lies at the intersection of cutting-edge technology and human ingenuity. From gravitational wave detectors that listen to the ripples in space-time to AI algorithms that piece together fragments of data into coherent maps, we're witnessing a revolution in how we explore the universe. And this journey is far from over. Every new discovery peels back another layer of mystery, revealing questions we didn't even know to ask. That's what makes interstellar cartography so exhilarating. It's not just about filling in blank spaces on a map. It's about stepping into the unknown and discovering what the universe has been hiding all along. The story of interstellar cartography begins not with high-tech telescopes or supercomputers, but with simple pencil sketches on paper. In the early 20th century, astronomers like Edwin Hubble peered through modest telescopes, painstakingly recording faint smudges of light they called island universes. These smudges turned out to be entire galaxies, each containing billions of stars, revealing a universe far grander than anyone had dreamed. Hubble's hand-drawn diagrams of spiral nebulae were the first rough drafts of a cosmic map we're still filling in today. What's astonishing isn't just how much we've discovered since then, but how much we got wrong along the way. For decades, scientists debated whether the Milky Way was the entire universe. The idea of mapping other galaxies seemed as fantastical as drawing a blueprint for a dream. But when Hubble proved Andromeda was a separate galaxy, nearly 2.5 million light-years away, it cracked open a new frontier. Suddenly, the universe wasn't just bigger, it was dynamic, evolving, and full of uncharted territories. Fast forward to today, and the tools we use would leave those early astronomers speechless. Modern sky surveys like the Sloan Digital Sky Survey have catalogued hundreds of millions of galaxies, while space telescopes like Hubble and Webb reveal details sharper than Hubble's namesake could have imagined. But perhaps the most revolutionary shift isn't in the hardware, it's in how we process the data. Machine learning algorithms now sift through petabytes of observations, spotting patterns no human eye could catch. They've helped us build three-dimensional atlases of the cosmos, where galaxies cluster like cities along vast filaments of dark matter. Yet for all our progress, the maps we're making today might look primitive a century from now. Right now, we're like 16th century explorers sketching coastlines without knowing what lies inland. Take the recent discovery of dark galaxies, entire systems made mostly of invisible matter, detectable only by their gravitational fingerprints. Or the mysterious cosmic web, where galaxies align in sprawling networks that mimic neural pathways in a brain. These aren't just new places to pin on a map. They're clues that the universe's true structure might be stranger than we ever guessed. The beauty of interstellar cartography is that every answer reveals deeper questions. When Hubble proved galaxies existed, no one knew they were fleeing from each other in an expanding universe. Today, as we map the large-scale structure of space, we're uncovering hints of forces even darker than dark matter. Perhaps evidence of parallel universes or dimensions we can't yet perceive. The maps we draw now are less about marking borders and more about discovering how little we truly understand. And that's what makes this journey so extraordinary. We're not just charting space, we're decoding the story of everything. To map the cosmos, you need tools as extraordinary as the universe itself. And today's interstellar cartographers wield instruments that border on magic. Take the James Webb Space Telescope, a technological marvel so sensitive it can detect the heat signature of a bumblebee on the moon. While Hubble showed us galaxies in stunning detail, Webb peers even farther, capturing light from the universe's infancy, galaxies forming just a few 100 million years after the Big Bang. Then there's the Chandra X-ray Observatory, which doesn't just see visible light but reveals the violent, high-energy universe. Black holes devouring stars, neutron stars spinning at dizzying speeds, and gas clouds hotter than 1,000,000 suns. But telescopes are only part of the story. The real heavy lifting happens on Earth, where supercomputers crunch numbers that would take a human lifetime to calculate. Imagine mapping an invisible city by tracking the footsteps of its inhabitants. That's how scientists use supercomputers to reconstruct the cosmic web of dark matter. By simulating the gravitational pull of this mysterious substance, they've revealed a hidden skeleton stretching across the universe, with galaxies clinging to its filaments like dew on a spider's web. What's even more remarkable is that you don't need a PhD to contribute to this grand project. Platforms like Galaxies Zoo invite everyday stargazers to help classify galaxies, turning cosmic cartography into a global collaboration. Thousands of volunteers have spotted rare galactic mergers, oddball star clusters, and even entirely new types of celestial objects, proof that mapping the universe is a human endeavor as much as a scientific one. Yet for all their power, these tools have limits. Some corners of the cosmos remain stubbornly out of reach, like regions so dense with dust that even infrared light can't penetrate. Others are so distant their light hasn't reached us yet, meaning parts of our cosmic map will always be blank, waiting for future generations to fill them in. But that's the thrill of exploration. Every tool we invent, every dataset we analyze, brings us one step closer to seeing the universe not as a collection of isolated wonders, but as a connected whole. And who knows what we'll find when the next breakthrough sharpens our view even further. Dark matter is the universe's greatest disappearing act, an invisible architect shaping everything we see, yet vanishing the moment we try to look directly at it. Imagine building a house and only ever seeing the furniture inside, never the beams holding up the walls. That's the puzzle astronomers face. How do you map something that refuses to interact with light, something that doesn't absorb, reflect, or emit a single photon? The answer lies in the one force it can't hide from: gravity. When light from a distant galaxy travels toward us, it doesn't always move in a straight line. If there's a massive cluster of dark matter in its path, the light bends around it like a car swerving to avoid an invisible obstacle. This phenomenon, called gravitational lensing, lets scientists trace dark matter's presence by studying the warped images of galaxies behind it. It's like watching ripples on a pond to deduce the shape of a submerged rock. These observations have revealed something astonishing. Dark matter isn't scattered randomly. It forms an intricate cosmic scaffold with galaxies perched along its threads like pearls on a necklace. But here's where it gets even stranger. Dark matter doesn't just hold galaxies together, it dictates how they move. Stars on the outer edges of spiral galaxies rotate so fast that they should fling into space, yet something unseen grips them tightly. Without dark matter's gravitational glue, galaxies would tear themselves apart. This invisible framework even influences the universe's largest structures, guiding galaxy clusters as they collide in slow-motion dances that last billions of years. The more we learn, the more questions arise. Why does dark matter clump in certain ways but avoid others? Could it be made of undiscovered particles, or does it hint at flaws in our understanding of gravity itself? Some theories suggest entire dark galaxies might exist, composed almost entirely of this enigmatic substance, floating undetected in the void. Others propose that dark matter interacts with itself in ways we haven't yet imagined, creating hidden currents or even dark weather patterns across the cosmos. What's clear is that dark matter isn't just a missing piece of the puzzle. It's a reminder that the universe operates on rules we're still deciphering. Every map we create of its distribution brings us closer to answering one of science's biggest mysteries. What is the true nature of reality? And with each discovery, we're not just filling in blanks on a chart. We're rewriting the story of how the cosmos builds itself. Some of the universe's most elusive travelers don't follow the rules. They roam the darkness alone, untethered to any star. Rogue planets drift through the void like cosmic nomads, invisible to traditional telescopes because they emit no light of their own. Yet these wandering worlds are far from rare. Astronomers estimate there could be billions of them silently threading through our galaxy, outnumbering stars by as much as 20 to 1. How do you find something that gives off no glow? The answer lies in a celestial phenomenon called microlensing. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the star's light like a lens, just for a fleeting moment. It's as if the universe winks at us, offering a brief glimpse of these shadowy travelers before they vanish back into the dark. What's astonishing isn't just their abundance, but their origins. Some rogue planets may have formed in the chaos of young solar systems, flung into the abyss by gravitational tugs of war between sibling planets. Others could have started life as failed stars, objects too small to ignite nuclear fusion, doomed to wander forever. There's even speculation that some might carry subsurface oceans, kept liquid by geothermal heat, turning them into potential havens for life adrift between the stars. Imagine an entire biosphere evolving in eternal night, untethered from the warmth of a sun. Mapping these wanderers isn't just about cataloging cosmic oddities. Their paths are like fingerprints, preserving clues about the violent dynamics of planetary formation. By studying their trajectories, scientists can reconstruct the gravitational storms that shaped early solar systems, like piecing together a car crash by tracing the skid marks. Some rogue planets might even be interstellar hitchhikers, ejected from other galaxies entirely, carrying secrets from realms beyond the Milky Way. Yet for all we're learning, rogue planets remind us how much remains hidden. They're the universe's way of whispering that for every bright star we chart, there are countless unseen worlds slipping through the cracks of our maps. And that's what makes them so fascinating. They're not just celestial drifters. They're proof that the cosmos still holds mysteries we've only begun to touch. The universe doesn't sprawl randomly. It's meticulously organized, woven together by an invisible scaffolding of cosmic filaments. Picture these as interstellar freeways, stretching millions of light years across the void, connecting galaxies like bustling cities along an endless interstate. But these aren't just empty roads. They're rivers of superheated gas and dark matter, pulsing with energy, ferrying the raw materials that birth stars and shape entire galaxies. Without them, the cosmos would be a scattered, disjointed place, a puzzle with half its pieces missing. What's incredible isn't just their scale, but how they shape everything we see. When the universe was young, mere fractions of a second after the Big Bang, tiny quantum fluctuations left imprints in spacetime. Over billions of years, gravity amplified those faint ripples into the vast filaments we detect today. They're the universe's original blueprints, guiding galaxies into clusters and superclusters with eerie precision. Imagine throwing a handful of sand onto a vibrating drum. The grains would gather along the resonant patterns. That's exactly how galaxies collect along these cosmic threads, drawn together by the gravitational hum of the filaments beneath them. But how do you map something so ethereal? Scientists use a combination of cutting-edge simulations and real-world observations. Supercomputers recreate the universe's evolution from its fiery infancy, tracing how dark matter's gravitational pull sculpted these filaments over eons. Meanwhile, telescopes like the European Space Agency's Planck satellite detect faint distortions in the cosmic microwave background, the afterglow of the Big Bang, revealing where these filaments tug on the fabric of space. It's like reconstructing an ancient road network by studying the wear patterns left on centuries-old trade routes. The most astonishing part, these filaments aren't passive. They're dynamic, pumping gas into galaxies like lifeblood. When two filaments intersect, the collision can ignite frenzied star formation, turning quiet galactic neighborhoods into stellar nurseries. Some researchers even speculate that these junctions might host the universe's most massive black holes, lurking where the cosmic currents converge. It's a reminder that the emptiness of space is an illusion. What looks like void is actually a throbbing network of energy and matter, humming with activity just beyond our sight. Yet for all we've uncovered, cosmic filaments hold deeper mysteries. Why do some stretch perfectly straight for millions of light years while others twist like cosmic DNA? Could they be conduits for unknown forces or particles we haven't yet discovered? Every answer peels back another layer, revealing just how much of the universe's grand design remains hidden in plain sight. And that's the magic of mapping them. We're not just charting space, we're decoding the universe's hidden circulatory system, one filament at a time. Finding planets in our own galaxy was hard enough, but spotting them in other galaxies. That's like trying to read a license plate on a speeding car halfway across the country. For decades, the idea seemed pure fantasy. The distances are so vast, the stars so faint, that even the most powerful telescopes couldn't pick out a tiny planet's silhouette against its host star. But then astronomers stumbled upon a cosmic loophole, gravity itself. When a massive object like a star or black hole passes between us and a distant light source, its gravity bends and magnifies that light like a lens. This phenomenon, called gravitational microlensing, doesn't just reveal hidden stars, it can uncover planets orbiting them, even from billions of light years away. The first confirmed exoplanet beyond the Milky Way wasn't some Earth-like world or gas giant. It was a rogue, a free-floating planet in the Whirlpool Galaxy, untethered to any star, detected only because its gravity briefly brightened the light of a star behind it. Think of it as the universe's version of a shadow puppet. For a fleeting moment, the planet's presence cast a detectable ripple in spacetime. Since then, microlensing has hinted at even stranger discoveries. In the Andromeda Galaxy, astronomers spotted what might be a planet orbiting a binary star system, a world with two suns like Tatooine from Star Wars, but on an intergalactic scale. What's mind-blowing isn't just that these planets exist, but how different they might be. In the Milky Way, we've found molten lava worlds, diamond planets, and super-Earths with skies thick enough to swim through. But other galaxies have different chemical recipes. Some are richer in heavy elements, potentially birthing planets with exotic materials we've never seen. Others might host hyper-dense worlds forged in the aftermath of galactic collisions, where the very rules of planetary formation could be rewritten. Imagine a planet with a crust made of neutron star remnants, or an atmosphere laced with elements forged solely in the hearts of distant quasars. Yet the real revolution isn't just in the discoveries, it's in how they're reshaping our cosmic perspective. If planets are this abundant in other galaxies, it suggests that planet formation isn't just a local quirk of the Milky Way. It's universal, a fundamental part of how galaxies evolve, and that raises an even bigger question. If planets are everywhere, could life be too? We're still decades away from having telescopes powerful enough to sniff out biosignatures in distant galaxies, but the mere possibility changes the game. Suddenly, the search for life isn't confined to our galactic backyard. It's a canvas as wide as the universe itself. Of course, mapping these worlds comes with staggering challenges. Microlensing events are fleeting, sometimes lasting just hours. There's no second chance to observe them, and distinguishing a planet's signal from the noise of interstellar dust, stellar flares, or even glitches in our own instruments is like picking out a whisper in a hurricane. But new tools are rising to the task. Next-generation space telescopes, combined with AI that can predict lensing events before they happen, might soon turn these needle-in-a-haystack discoveries into a routine catalog. What's clear is that we're standing at the edge of a new frontier. For centuries, we've wondered if other stars had planets. Then we wondered if those planets could harbor life. Now we're asking those same questions not just about other stars, but other galaxies. And with every distant world we add to the map, the universe feels a little less lonely and a whole lot more mysterious. There's something out there, an unseen force so powerful it's tugging our entire galaxy and thousands of others toward it at over 2 million kilometers per hour. Astronomers call it the Great Attractor, and despite decades of searching, its true nature remains one of the cosmos' most tantalizing puzzles. Picture a river flowing toward a hidden waterfall, but instead of water, it's a current of galaxies, including our own, being pulled relentlessly toward a point in space we can't even see. The reason? It lies directly behind the Milky Way's crowded central bulge, obscured by thick clouds of dust and stars that block our view like a cosmic blindfold. What makes this mystery even stranger is the sheer scale of the force at work. The Great Attractor's gravitational pull suggests something with the mass of tens of thousands of Milky Ways clustered together. At first, scientists assumed it must be a colossal supercluster of galaxies, but when they mapped the region with X-ray telescopes piercing through the dust, they found far fewer galaxies than expected. The math didn't add up. It was like hearing a roar in the jungle and finding only a kitten when you pushed aside the leaves. Then came a breakthrough. By studying the subtle motions of thousands of galaxies, researchers realized the Great Attractor isn't acting alone. It's just one piece of an even vaster structure called the Laniakea Supercluster. Imagine a sprawling metropolis where galaxies are the buildings, and the Great Attractor is downtown, the gravitational heart pulling everything toward it. Laniakea, which means immense heavens in Hawaiian, stretches over 500 million light-years and contains roughly 100,000 galaxies, all drifting together in a slow cosmic dance. But here's where it gets even more intriguing. Some theorists suggest the Great Attractor might not be the final destination. Beyond Laniakea, there's evidence of something even larger, a gravitational anomaly nicknamed the Shapley Attractor, pulling our supercluster toward it like a matryoshka doll of cosmic forces. Others speculate that dark energy, the mysterious force accelerating the universe's expansion, could be warping space-time in ways that mimic concentrated mass, creating illusions of phantom attractors. The hunt for answers is far from over. New radio telescopes like the Square Kilometre Array are tuning into frequencies that can see straight through the Milky Way's dust, while advanced simulations track the universe's large-scale flows like weather models for the cosmos. Every clue brings us closer to understanding not just where we're headed, but how the universe organizes itself on the grandest scales. And that's what makes this quest so thrilling. It's not just about solving a single mystery. It's about uncovering the hidden machinery that shapes everything we see, and perhaps discovering forces we haven't even imagined yet. Imagine holding a photograph not just of your childhood, but of the universe's a snapshot taken when the cosmos was a mere 380,000 years old. That's exactly what the cosmic microwave background gives us, a glowing imprint of the infant universe frozen in time. It's not just ancient light, it's a fossilized whisper of the Big Bang's aftermath, carrying secrets about how everything, galaxies, stars, even the very fabric of space began. What makes this glow so special isn't just its age, but its near-perfect uniformity. Across the entire sky, the CMB's temperature hovers just above absolute zero, at about 2.7 degrees Kelvin. But look closer and you'll spot faint ripples, tiny variations in temperature, some as small as 1 part in 100,000. These aren't random flaws. They're cosmic blueprints, the gravitational fingerprints of density fluctuations that would one day grow into galaxies and superclusters. It's like examining the grooves on a vinyl record and realizing they encode the symphony of the universe's structure. The most stunning revelations come from missions like the Planck satellite, which mapped these temperature variations with such precision that they resemble a pointillist painting of the early cosmos. Planck's data confirmed predictions with remarkable accuracy, but it also threw curveballs, one glaring anomaly, the so-called axis of evil, a mysterious alignment of temperature fluctuations that seemed to defy the cosmological principle, the idea that the universe should look the same in all directions. It's as if the universe has a preferred orientation, a cosmic north that shouldn't exist. Then there's the cold spot, a bizarre, sprawling region in the CMB significantly cooler than its surroundings. Some theories suggest it could be a bruise left by a collision with another universe during inflation, while others argue it's a statistical fluke. Either way, these quirks hint that our understanding of the universe's infancy might be missing crucial chapters. But the CMB isn't just about temperature. Polarization patterns in the light, like the subtle swirls in a cup of coffee, carry clues about primordial gravitational waves, ripples in space-time from the universe's explosive birth. Detecting these waves would be like hearing the echo of the Big Bang itself, offering proof of cosmic inflation, the theory that the universe expanded faster than light in its first fleeting moments. What's astonishing is how much we've decoded from this ancient afterglow. By studying its patterns, we've calculated the universe's age 13.8 billion years, its composition 5% ordinary matter, 27% dark matter, and 68% dark energy, and even its ultimate fate. Yet every answer uncovers deeper puzzles. Why does the CMB's large-scale structure seem slightly off? Could there be traces of a universe before ours etched into its light? The more we map this primordial glow, the more it feels like reading a diary with half the pages torn out, each visible word hinting at untold stories. And that's the magic of the cosmic microwave background. It's not just a relic, it's a living archive still whispering secrets across billions of years. As new telescopes probe its subtlest details, we're not just looking back in time. We're piecing together the origin story of everything, one faint, ancient photon at a time. Galactic collisions are the ultimate cosmic slow-motion ballet, a dance that unfolds over billions of years, where gravity choreographs every move. Right now, our Milky Way is locked in a gravitational embrace with the Andromeda Galaxy, inching closer at 110 kilometers per second. But this isn't a rare catastrophe, it's a routine chapter in the life of galaxies. Across the universe, galaxies merge, twist, and consume one another in a process astronomers call galactic cannibalism. And far from being destructive, these collisions are creative forces, forging new structures from the chaos. Picture two galaxies drifting into each other's gravitational pull. At first, they might pass harmlessly like ships in the night, but gravity doesn't let go. Over eons, their mutual attraction pulls them back, sending them into a series of looping orbits. Stars spread so thinly that direct collisions are rare, slide past one another like ghosts. Yet the galaxy's shapes warp dramatically, stretched into long tidal tails that glitter with stolen starlight. Meanwhile, vast clouds of gas and dust slam together, triggering explosive waves of star formation stellar fireworks lighting up the cosmic night. These mergers don't just reshape galaxies, they rewrite their very identities. When a small galaxy falls victim to a larger one, it's torn apart, its stars absorbed into the winner's halo. Our own Milky Way bears the scars of past meals, with streams of stars, remnants of devoured dwarf galaxies still tracing their doomed orbits. But sometimes the result isn't a clear victor. When two spiral galaxies of similar size collide, their delicate disks are shredded, and the wreckage settles into a new form, an elliptical galaxy, a featureless sphere of aging stars. This is likely the fate awaiting the Milky Way and Andromeda, a future merger that will erase their iconic spirals, leaving behind a single, bloated galaxy nicknamed Milkdromeda. The real magic happens in the invisible realm. Dark matter, which outweighs visible matter 5 to 1, dictates the dance's rhythm. During a merger, dark matter halos interpenetrate, their gravitational tug warping the paths of stars and gas. Simulations reveal how these halos stretch into vast, diffuse clouds, while galaxies' visible components lag behind, caught in the drag of their own inertia. It's like watching smoke swirl in the wake of a passing hand, the visible tracer of an unseen force. What's astonishing is how much these collisions reveal about the universe's hidden rules. By studying merging galaxies, astronomers have confirmed the existence of dark matter, measured its distribution, and even glimpsed how it might interact with itself. Collisions also serve as cosmic laboratories, forging extreme environments where black holes grow to unimaginable sizes and magnetic fields twist into colossal filaments. Yet the most profound lesson might be this: destruction and creation are two sides of the same coin. Without galactic cannibalism, the universe would lack its richest structures: no giant ellipticals, no galaxy clusters, no supermassive black holes anchoring the cosmic web. Even our own solar system owes its existence to an ancient merger that stirred up the gas and dust from which the sun and planets formed. So while the thought of the Milky Way's eventual demise might seem unsettling, it's also a reminder we're not just observers of the cosmos. We're products of its endless star-splattered collisions. Between the glittering superclusters and filaments of the cosmic web lie the universe's most desolate landscapes, regions so empty they defy intuition. These cosmic voids aren't just pockets of space with fewer galaxies. They're staggering abysses spanning hundreds of millions of light years, where the density of matter can be less than 1/10 the cosmic average. If the universe's structure resembles a sponge, these voids are the holes, not just gaps, but active participants shaping how everything evolves. What's fascinating isn't just their scale, but how they form. In the early universe, tiny quantum fluctuations created slightly denser regions where matter clustered, and slightly emptier zones where it drained away. Over billions of years, gravity amplified this contrast, pulling galaxies toward the densest areas like water rushing downhill, leaving behind these ever-growing deserts. But here's the twist: voids aren't static. They expand faster than the universe itself, their emptiness creating a gravitational repulsion that pushes surrounding matter away. It's as if space itself is fleeing from nothingness. The eeriest part, these voids aren't completely barren. Floating within them are void galaxies, lone wanderers that somehow avoided being swept into the cosmic crowds. These isolated survivors often look different from their cluster-dwelling cousins, with slower rates of star formation and older stellar populations. Some astronomers call them red and dead galaxies, frozen in time because they lack fresh gas to fuel new stars. Studying them is like finding a single tree thriving in the middle of a desert, proof that even the emptiest places hold secrets. Yet voids challenge our theories in profound ways. Their sheer size and growth rate suggest dark energy. The mysterious force accelerating cosmic expansion might work differently in these regions. Some models even propose that voids could contain exotic forms of dark matter or energy we haven't accounted for, subtly warping spacetime in ways we're only beginning to detect. Then there's the void phenomenon problem. Simulations consistently predict more small voids than we actually observe, as if the universe has a preference for keeping its empty spaces extra large. Mapping these voids isn't just academic, it's rewriting the story of cosmic evolution. By analyzing their shapes and distributions, scientists have uncovered evidence that voids may have played a key role in creating the cosmic microwave background's temperature variations. They've also revealed a bizarre pattern. Voids tend to align with one another across vast distances, as if connected by invisible threads. This discovery hints at processes operating on scales so large they dwarf even the filamentary structures we thought defined the universe's architecture. Perhaps the most humbling realization is that we're floating in one of these voids right now. The Milky Way resides in the local void, a region about 150 million light-years across. Far from being a cosmic backwater, our position gives us a front-row seat to observe how emptiness shapes the universe. And that's the ultimate lesson of voids. They're not just empty space waiting to be filled. They're dynamic actors in the cosmos, sculpting the destiny of everything we see. Gravitational waves are the universe's hidden messengers, ripples in the fabric of space-time itself, carrying whispers of the most violent events in the cosmos. Unlike light, which can be absorbed, scattered, or blocked, these waves travel unimpeded across billions of light-years, offering a pristine window into phenomena we'd otherwise never detect. When two black holes spiral into each other, their collision sends shockwaves through space-time like tremors from an earthquake. The same happens when neutron stars, city-sized remnants of dead stars, clash in explosions so intense they forge gold and platinum in their wake. These aren't just cosmic fireworks, they're brushstrokes on a new kind of map, one drawn not in light but in the warp and weft of space-time. The first time we heard gravitational waves was in 2015, when LIGO laser interferometers caught the faint chirp of two black holes merging over 1 billion light-years away. That detection was like stumbling upon a new sense suddenly. The universe wasn't just something we could see. It was something we could feel. Since then, LIGO and its European counterpart, Virgo, have catalogued dozens of these events, each revealing surprises. Some black holes are far heavier than theories predicted. Others spin at dizzying speeds, hinting at chaotic origins, and neutron star mergers. They're cosmic alchemy labs, ejecting clouds of heavy elements that later seed new planets and perhaps life. But gravitational waves aren't just about spotting collisions. They're about mapping the invisible. Take dark matter. If some of it lurks in primordial black holes, those forged in the universe's first, second gravitational waves could be our only way to find them. Or consider supermassive black holes, the monsters at the heart of galaxies. When their host galaxies merge, these giants should spiral together, emitting waves so low frequency they'd take decades to oscillate. Future observatories like LISA, a space-based detector, will tune into these deep cosmic hums, tracing the growth of black holes across cosmic time. The real revolution lies ahead. Imagine a network of gravitational wave observatories spanning the solar system, each acting like a microphone picking up spacetime's vibrations from different angles. Combined, they could pinpoint events with astonishing precision, letting telescopes swivel to catch the afterglow. This synergy, dubbed multi-messenger astronomy, has already paid off. In 2017, a neutron star merger's gravitational waves arrived just before a gamma-ray burst and a glowing kilonova, confirming theories about the origins of heavy elements. Soon, we might track rogue black holes drifting between galaxies, or even detect echoes from the Big Bang itself, ripples from the universe's birth still resonating through space-time. What's thrilling isn't just the discoveries we've made, but how much we've yet to learn. Gravitational waves could reveal hidden dimensions, test Einstein's relativity in extreme environments, or uncover entirely new classes of objects. They're not just adding to our cosmic map, they're rewriting its very language. And as our detectors grow more sensitive, we're not just listening to the universe anymore. We're feeling its heartbeat. Fast radio bursts are the universe's most enigmatic signals, brief, blazing flashes of radio waves that outshine entire galaxies for just milliseconds before vanishing without a trace. First discovered in 2007, these cosmic bursts arrive from billions of light years away, packing as much energy as the sun emits in decades. What's baffling isn't just their power, but their unpredictability. Some burst once and never repeat, like a gunshot echoing across the cosmos. Others flicker on and off in erratic patterns, teasing astronomers with clues they can't quite decipher. Tracking their origins is like trying to find a lighthouse in a hurricane. The bursts travel so far that their radio waves get stretched and scattered by interstellar plasma, making it nearly impossible to trace them back to their source. But new radio telescopes are changing the game. Facilities like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, scan vast swaths of sky every night, catching these fleeting signals in real time. When a burst is detected, observatories worldwide pivot to study it across multiple wavelengths, hunting for any hint of what caused it. The leading suspect. Magnetars, super dense, highly magnetized remnants of exploded stars that occasionally unleash catastrophic starquakes, cracking their crusts and releasing torrents of energy. In 2020, astronomers got their first smoking gun when a magnetar in our own galaxy emitted a burst eerily similar to a fast radio burst, albeit much weaker. But here's the catch: not all bursts fit this mold. Some repeat with no discernible pattern, while others appear to originate from regions devoid of any known magnetars. That's where the theories get wild. Could some bursts come from colliding neutron stars, or perhaps cosmic strings, hypothetical defects in spacetime left over from the Big Bang? Then there's the most speculative idea of all, alien megastructures. Some scientists have floated the possibility that highly advanced civilizations might use focused radio beams to propel light sails across interstellar distances, with Earth occasionally catching a fleeting glimpse of these transmissions. While there's zero direct evidence for this, the mere fact that it's even considered shows just how mysterious these bursts remain. What's clear is that fast radio bursts aren't just cosmic oddities, they're tools. As these waves traverse the universe, they interact with the sparse matter between galaxies, allowing scientists to measure the universe's missing baryonic matter, a long-standing mystery in cosmology. Each burst is like a flashlight beam passing through fog, illuminating the invisible structure of the cosmos. The deeper we look, the stranger the picture becomes. Some bursts exhibit bizarre polarization patterns, suggesting they traveled through extreme magnetic fields. Others arrive with a telltale frequency sweep, a fingerprint of their journey through intergalactic space. And in rare cases, repeating bursts show periodic activity cycles, hinting at orbital motion around a companion object. Every new detection raises more questions than answers, and that's what makes this hunt so exhilarating. Fast radio bursts remind us that the universe is still full of unsolved puzzles, lurking just beyond the edge of our understanding. One thing's certain: when we finally crack their code, it won't just reveal the source of these brilliant flashes. It'll open a whole new window into the most extreme environments the cosmos has to offer. Quasars are the universe's ultimate powerhouses, cosmic monsters so bright they outshine entire galaxies, yet so compact they'd fit inside our solar system. At their core lies a supermassive black hole, millions to billions of times heavier than our Sun, surrounded by a swirling disk of doomed gas and dust. As this material spirals inward at nearly light speed, friction heats it to millions of degrees, transforming the disk into an unbelievably bright beacon visible across the cosmos. What makes quasars truly special isn't just their ferocity, but their role as time machines. The light from the most distant quasars has traveled over 13 billion years to reach us, showing us the universe when it was less than 1 billion years old, a mere infant compared to its current age. These ancient lighthouses reveal secrets about the universe's darkest era, the cosmic dawn. Before the first stars fully lit up the cosmos, space was filled with a fog of neutral hydrogen gas that absorbed ultraviolet light. But quasars, with their incredible energy, acted like cosmic blowtorches, ionizing this fog and carving transparent bubbles in space. By mapping where these bubbles formed, astronomers can trace how light gradually permeated the universe, ending the so-called Dark Ages. It's like finding charred marks on a cave wall and realizing they tell the story of the first fire ever lit. Yet quasars aren't just relics. Their distribution across space forms a three-dimensional map of the universe's large-scale structure. When scientists chart thousands of quasars, they reveal a web-like pattern where galaxies cluster along invisible filaments of dark matter. Some quasars even appear in tight groups, suggesting their host galaxies are colliding, a violent process that may explain how supermassive black holes grew so quickly in the early universe. This clustering gives us clues about dark energy's influence on cosmic expansion and how gravity sculpted the cosmos over billions of years. The most mind-bending quasars challenge our understanding of physics. Some emit jets of plasma stretching millions of light years, longer than the distance between galaxies, moving at over 99% the speed of light. Others flicker unpredictably, hinting at chaotic feeding patterns or even black holes orbiting each other in a deadly dance. Then there's the mystery of how these giants formed so soon after the Big Bang. Current theories struggle to explain how black holes grew so massive so quickly, leading some scientists to speculate about exotic possibilities like direct collapse black holes, objects born not from stars, but from the outright collapse of primordial gas clouds. What's remarkable is how these distant beacons still shape modern astronomy. When quasars' light passes through intergalactic clouds, it gets subtly altered, leaving absorption lines that act as chemical fingerprints. This cosmic barcode lets astronomers inventory the universe's elemental makeup across cosmic time, revealing how heavy elements gradually enriched space. Other quasars serve as natural telescopes, their gravity bending background light into multiple images, a phenomenon called gravitational lensing that magnifies even fainter objects behind them. Quasars prove that sometimes the most violent objects make the best guides. They illuminate not just their immediate surroundings, but the entire history of the cosmos, from its first moments of light to the vast web of galaxies we see today. And with every new quasar discovered, we're not just adding another dot to the map. We're uncovering another piece of the puzzle that explains how darkness gave way to light and chaos transformed into structure. Beyond the familiar planets, past the last gas giant Neptune, lies a frozen frontier where sunlight is barely a memory, the Kuiper Belt. This vast donut-shaped region is home to icy relics from the solar system's birth, including Pluto, once considered our 9th planet. But Pluto isn't alone out here. Dwarf planets like Haumea, shaped like a squashed football from its rapid spin, and Makemake, with its eerie lack of atmosphere, orbit alongside it. Then there's Sedna, a mysterious reddish world so distant it takes 11,000 years to complete a single trip around the Sun. Its elongated orbit is so extreme that some scientists believe it could be pointing the way to something even more astonishing, an undiscovered giant planet lurking in the darkness. The Kuiper Belt isn't just a graveyard of frozen leftovers. It's a time capsule preserving the raw ingredients of planetary formation. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a shockingly active world with nitrogen glaciers, towering ice mountains, and even possible cryovolcanoes spewing slushy ice. The discovery shattered assumptions that these distant worlds would be inert and geologically dead. Instead, they're dynamic, sculpted by processes we're only beginning to understand. But the real mystery lies beyond. Far past the Kuiper Belt, astronomers hypothesize the existence of the Oort cloud, a spherical shell of icy bodies stretching up to a light year from the Sun. This is where long-period comets like Hale-Bopp originate, slingshotting inward when gravitational nudges disturb their orbits. The Oort cloud is so distant and diffuse that we've never directly observed it, yet its gravitational fingerprints are everywhere, shaping the paths of comets that occasionally blaze through our night skies. The most tantalizing clue hiding in this frozen wilderness: the peculiar orbits of several extreme Kuiper Belt objects, all tilted and clustered in ways that defy normal gravitational explanations. In 2016, astronomers Konstantin Batygin and Mike Brown crunched the numbers and found these odd orbits could be explained by the pull of an undiscovered planet 5 to 10 times Earth's mass, dubbed Planet 9. This hypothetical world would orbit so far out that it could take 10 to 20,000 years to circle the Sun, making it nearly invisible to current telescopes. The hunt for Planet 9 has turned into one of astronomy's greatest detective stories. Researchers are scanning the skies with some of Earth's most powerful telescopes, while others run simulations to narrow down where this elusive giant might hide. Some theories suggest it could be a rogue planet captured by the Sun's gravity, or even a primordial black hole the size of a grapefruit. Whatever it is, its discovery would rewrite our understanding of the solar system's outer limits and remind us that even in our cosmic backyard, there are still worlds waiting to be found. What's certain is that the Kuiper Belt and beyond aren't just empty wastelands. They're active, evolving regions that hold keys to our solar system's past and perhaps its future. Every new mission, every telescope pointed at these frozen frontiers brings us closer to answering fundamental questions. How did the planets form? Are there other hidden worlds orbiting unseen? And what other surprises lie in the darkness just beyond the edge of our maps? Interstellar dust might seem like a nuisance, tiny particles drifting through space, blotting out the light of distant stars like cosmic fog. But these microscopic grains are far more than just obstacles. They're the universe's hidden architects, shaping everything from the birth of stars to the chemistry of planets. Picture a snow globe shaken by invisible hands, where each flake is a speck of silicate or carbon, some no larger than a molecule. Together, they form vast, swirling clouds that stretch across light years, so dense in places that they blot out entire galaxies from view. Yet without this dust, the cosmos as we know it wouldn't exist. What's astonishing is how much these tiny particles influence the grandest processes in space. When a cloud of interstellar dust collapses under its own gravity, it doesn't just form stars, it kickstarts the creation of planetary systems. The dust grains act like seeds, clumping together into pebbles, then boulders, and eventually planets. Some of these grains are even laced with complex organic molecules, the precursors to life itself. That means the same dust that obscures our view might also carry the raw ingredients for biology across the galaxy. Mapping this dust has always been a challenge. Traditional telescopes see it as shadowy blobs, two-dimensional smudges that reveal little about their true structure, but new techniques are changing the game. By combining data from infrared observatories, radio telescopes, and even polarized light measurements, astronomers can now reconstruct dust clouds in 3 dimensions, peeling back their layers like a cosmic onion. These maps reveal intricate filaments and cavernous bubbles, sculpted by stellar winds and supernova explosions. Some regions resemble towering mountains, while others sprawl like delicate lace, their shapes hinting at the violent forces that shape them. The most surprising discovery: dust isn't evenly distributed. It clumps in ways that defy simple models, with some clouds so porous they're practically invisible, while others are dense enough to hide newborn stars. This patchiness affects how we measure distances in space, skewing our estimates of how far away certain galaxies really are. Imagine trying to gauge the height of a mountain through a hazy fog, only the fog keeps changing thickness. That's the challenge astronomers face when accounting for interstellar dust in their cosmic cartography. Yet for all its frustrations, dust also offers opportunities. Certain wavelengths of light, like infrared, can pierce through these clouds, revealing what lies behind them. The James Webb Space Telescope excels at this, using its infrared eyes to peer into stellar nurseries that were once impenetrable. And because dust absorbs and re-emits light in predictable ways, it can serve as a tracer for otherwise invisible phenomena, like magnetic fields twisting through space or shockwaves from ancient supernova. Perhaps the most poetic revelation is that we're made of this stuff too. The iron in your blood, the calcium in your bones, these elements were forged in dying stars and then scattered across the galaxy by stellar winds, riding dust grains until they found their way into Earth's primordial soup. So the next time you look up at a dark, dusty patch in the night sky, remember, you're not just seeing an obstacle, you're staring at the raw materials of worlds and maybe, just maybe, the origins of life itself. We're floating inside a cosmic bubble, not a metaphor, but a real, 1,000-light-year-wide cavity in space, sculpted by the violent deaths of massive stars. This is the local bubble, our galactic neighborhood, and its story reveals how destruction can pave the way for life. Picture a vast, irregular sphere of hot, sparse gas surrounding our solar system. its walls lined with young stars and glowing nebulae, all born from the same cataclysms that hollowed out this space. The local bubble didn't form by chance. Roughly 10 to 20 million years ago, a chain reaction of supernova exploding stars dozens of times more massive than our Sun detonated like cosmic grenades in our corner of the Milky Way. Each blast wave shoved interstellar gas outward, sweeping it into dense shells that eventually collapsed under gravity, igniting new generations of stars. Today, we see the aftermath in stellar nurseries like the Scorpius-Centaurus Association, where brilliant blue stars trace the bubble's edges like pearls on a string. These young giants will someday explode too, continuing the cycle of destruction and creation that shapes galaxies. What makes this bubble special isn't just its origin, but its emptiness. The space inside is about 10 times less dense than the surrounding galactic environment, filled with wispy, million-degree gas so thin that atoms rarely collide. This clarity has an unexpected benefit. It gives astronomers an unusually unobstructed view of distant galaxies, as if we're peering through a cosmic picture window. Without this clearing, much of the universe's light would be absorbed or scattered by intervening dust. But the local bubble's greatest gift might be its role in Earth safety. Supernova are deadly. A close-range blast could strip away our ozone layer, exposing life to lethal radiation. By clearing out nearby massive stars millions of years ago, those ancient explosions created a temporary safe zone. The nearest stars capable of going supernova today, like Betelgeuse, now sit safely beyond the bubble's edge. It's a striking paradox. The same violence that could have sterilized our planet instead carved out a protective harbor, buying time for complex life to evolve. Mapping the bubble's full structure remains a challenge. Unlike a soap bubble, its surface is ragged and porous, with tunnels branching into neighboring cavities like holes in Swiss cheese. Astronomers piece together its contours using 3D reconstructions of stellar motions and gas densities, revealing a dynamic, ever-changing shape. Some models suggest our solar system entered the bubble only 5 million years ago, riding a wave of galactic motion. Others propose the local bubble is merging with adjacent cavities, creating an even larger network of voids. This celestial soap opera isn't unique to our neighborhood. Similar bubbles pepper the Milky Way, evidence that supernova act as galactic landscapers, chiseling out cavities where future stars can form. Seen from afar, our galaxy's spiral arms might resemble froth on a cosmic cappuccino, each bubble a testament to the explosive cycles that keep galaxies alive. And that's the ultimate lesson of the local bubble. In the grand tapestry of space, even destruction serves a purpose. Without those ancient stellar explosions clearing the stage, the next act, the one that led to us, might never have begun. Galactic magnetic fields are the universe's invisible puppeteers, threading through space with such delicate precision they guide the birth of stars, steer cosmic rays, and even shape the spiral arms of galaxies. Unlike the obvious pull of gravity or the flash of starlight, these forces work in silence, leaving no visible trace, yet their influence is everywhere. Picture a vast, unseen loom weaving threads of magnetism through the cosmos, each strand thinner than a human hair but stretching tens of thousands of light years. Without them, galaxies would look and behave entirely different. Until recently, mapping these fields was like trying to sketch a storm's wind patterns by watching leaves flutter. But now, radio telescopes like the Atacama Large Millimeter Array are revolutionizing our view. By observing how dust grains align with magnetic fields like countless compass needles pointing the same direction, scientists can trace their structure in stunning detail. What they've found is astonishing. These fields aren't just background noise. They're dynamic, organized, and far stronger than anyone predicted. In some galaxies, magnetic forces rival gravity in shaping how gas collapses into stars, acting like cosmic traffic cops that direct the flow of matter. Take the Milky Way's own magnetic field, a sprawling web of energy that influences everything from the paths of high-energy particles to the formation of massive star clusters. Near the galactic center, the field twists into chaotic knots, tangled by the supermassive black hole's ferocious energy. Farther out, it smooths into elegant spirals, perfectly aligned with the galaxy's arms. This isn't just decoration, it's infrastructure. When interstellar gas gets compressed along these magnetic lanes, it triggers star birth like beads forming on a vibrating string. The most surprising revelation: these fields might be primordial, dating back to the universe's infancy. Some theories suggest they were forged in the Big Bang's aftermath, when the cosmos was a seething plasma of charged particles. As galaxies grew, they inherited these ancient magnetic threads, weaving them into their very fabric. Others argue that turbulent motions within galaxies could amplify weak seed fields over time, like a dynamo generating electricity. Either way, their persistence is a testament to how deeply magnetism is entwined with cosmic evolution. What's next in this magnetic revolution? Astronomers are now probing how these fields interact with dark matter, whether they can propel jets from black holes, and even if they played a role in guiding the universe's first stars to ignite. Every new map peels back another layer, revealing a universe far more intricate and interconnected than we ever imagined. So while we can't see these forces directly, their fingerprints are all around us, quietly shaping the story of everything. Something is wrong with our cosmic yardstick. For over a century, astronomers have measured how fast the universe is expanding, a number called the Hubble constant. But here's the problem: two of our most trusted methods keep giving different answers. It's like checking your speedometer and GPS simultaneously, only to find one says you're going 60 while the other insists it's 70. This discrepancy, known as the Hubble tension, isn't just a minor hiccup. It's a full-blown crisis that could mean we're missing something fundamental about how the universe works. The first method relies on the cosmic microwave background, that ancient afterglow from the Big Bang. By studying its subtle patterns, scientists can calculate how fast the infant universe was expanding, then use our models to predict today's rate. The result, about 67 kilometers per second per megaparsec. But when astronomers measure nearby galaxies directly, using pulsating stars called cepheids or exploding supernova as distance markers, they get a different number, roughly 73. That 6-kilometer gap might sound small, but over cosmic distances, it adds up to a glaring inconsistency. Either someone's math is off, or the universe is playing by rules we haven't discovered yet. What makes this tension so explosive is what it implies about dark energy, the mysterious force accelerating cosmic expansion. If our measurements are correct, dark energy might not be constant as we've assumed. It could be strengthening over time or interacting with dark matter in unexpected ways. Some theorists even speculate we're seeing hints of extra dimensions or exotic particles that alter gravity on cosmic scales. Others propose more radical ideas, like the possibility that we're living in a rare underdense region of space, skewing our local measurements like a funhouse mirror. The solution might lie in better maps. Right now, our galactic surveys are like trying to chart ocean currents with only a handful of buoys. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time aim to change that, cataloging billions of galaxies to trace the universe's expansion with unprecedented precision. By comparing how galaxy clusters move at different distances, astronomers hope to spot where our models break down. Will the tension vanish under this flood of new data, or will it deepen, forcing us to rewrite the textbooks? One thing's certain, the Hubble tension isn't just about numbers. It's a crack in the foundation of modern cosmology, a whisper that somewhere, hidden in the darkness, the universe still has secrets to share. And how we solve this puzzle could reshape our understanding of everything from the Big Bang to the fate of the cosmos itself. Exomoons might be the most promising real estate in the universe, hidden worlds orbiting distant planets, tucked away in the shadows where life could thrive unseen. Imagine an Earth-sized moon circling a gas giant in the habitable zone, its surface bathed in the gentle glow of reflected starlight, with tidal forces flexing its crust to power underground oceans. These aren't just sci-fi fantasies. Statistically, they should exist in staggering numbers, yet spotting them is like trying to find a firefly next to a spotlight while standing miles away. The challenge begins with their parents. Most exoplanets we've found were detected by the transit method, catching the faint dimming of a star as a planet passes in front of it. But a moon's signal is buried in the noise, a whisper lost in the shout of its host planet's shadow. Some moons might only block 1/10,000th of the star's light, a fluctuation smaller than the natural flickering of the star itself. So astronomers are getting creative. One approach hunts for telltale wobbles in the planet's transit timing. Just as the moon tugs on Earth, an exomoon would make its planet dance slightly off rhythm, arriving early or late in its orbit. These nanosecond deviations, measurable with next-gen telescopes, could betray a hidden companion. Then there's the gravity trick. When a moon and planet orbit each other, their shared center of mass shifts, distorting the star's light in predictable ways during a transit. It's like watching a pair of ice skaters spin while holding hands. Their combined motion leaves a unique imprint. The Hubble Space Telescope once caught a tantalizing hint of this around exoplanet Kepler 1625b, where a Neptune-sized moon might lurk, though the data remains controversial. But the real game-changer could be microlensing, where a star's gravity magnifies the light of a background star. If a planet and its moon pass through this cosmic lens, they create a double dip in brightness, a signature unlike anything else. Projects like the Nancy Grace Roman Space Telescope, launching later this decade, will scan for these events by the thousands, potentially uncovering moons too distant for other methods. Why go to such lengths? Because exomoons could be life's best hideouts. A gas giant's gravity might shield its moons from lethal radiation, while tidal heating could keep subsurface oceans liquid far beyond the traditional habitable zone. Look at Europa and Enceladus in our own solar system, frozen on the outside, potentially teeming beneath. Now imagine similar worlds orbiting exoplanets, their chemistry primed by the mix of stellar light and planetary magnetism. Some might even have atmospheres, detectable by the way they filter starlight during transits. The hunt is young, but the stakes are cosmic. Finding an exomoon wouldn't just add a pin to our galactic map, it would redefine where we look for life. And with every technological leap, we're not just searching for worlds anymore. We're peeling back the layers of possibility, one subtle wobble at a time. The universe is vast beyond comprehension, filled with hundreds of billions of galaxies, each home to trillions of planets. Statistically, the numbers suggest life should be everywhere. Yet when we scan the stars for signs of intelligence, all we hear is silence. This eerie contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the cosmos is so hospitable, why does it feel so empty? Consider the sheer scale of cosmic time. Our galaxy is over 13 billion years old, while human civilization has existed for a mere blink, less than 10,000 years. If even one advanced civilization arose millions of years before us, they could have colonized the Milky Way many times over. The math suggests we should see evidence of their existence, megastructures harnessing starlight, probes exploring distant worlds, or signals pulsing through space. Yet our telescopes and radio dishes catch nothing but the hum of natural phenomena. So where are they? One possibility is that life is far rarer than we think. Perhaps the conditions for intelligent life are so specific that even among billions of planets, we're alone. Or maybe civilizations inevitably self-destruct, wiped out by war, environmental collapse, or runaway technology before they can spread beyond their home world. There's another unsettling idea. Advanced societies might deliberately avoid contact, hiding from potential threats or observing us like a cosmic nature preserve. Then there's the zoo hypothesis, the notion that we're being intentionally isolated, either for our own protection or as part of some grand experiment. Others suggest we're simply too primitive to recognize the signs of a galactic community. Alien technology could operate on principles so advanced they're indistinguishable from natural phenomena to us. Imagine an ant trying to comprehend the internet. It might walk right over fiber optic cables without realizing their purpose. The paradox forces us to confront our own assumptions. Are we overestimating the longevity of civilizations, underestimating the dangers of space travel, or is the answer hidden in the gaps of our cosmic maps? Some regions of the galaxy might be more conducive to life than others, with Earth sitting in an unusually quiet neighborhood. Alternatively, the most advanced beings might have transcended physical form, uploading their consciousness into digital realms we can't detect. Every potential solution reveals another layer of mystery. The silence of the cosmos isn't just a puzzle, it's a mirror, reflecting how little we truly understand about life's place in the universe. And until we find definitive proof of others out there, the question remains, are we the first, the last, or simply the only ones asking? Imagine building a universe from scratch, not with stars and planets, but with lines of code and mathematical equations. That's exactly what cosmologists do when they fire up supercomputers to simulate the cosmos. These aren't just video game recreations, they're precision instruments, fine-tuned with real-world data to mimic the universe's evolution over billions of years. Every dark matter particle, every wisp of interstellar gas, every gravitational tug is accounted for in equations that would fill libraries if written out by hand. The result, a virtual cosmos so accurate it can predict where to point our telescopes next. Take the Illustris TNG project, one of the most ambitious simulations ever run. It models a cube of space over 13 billion light-years wide, tracking trillions of particles as they clump into galaxies, swirl into spiral arms, and collide in slow-motion mergers. The simulation doesn't just match what we see, it reveals patterns we've missed. For example, it predicted how magnetic fields would thread through galaxy clusters long before telescopes confirmed their presence. It's like having a time machine for the universe, letting scientists rewind and fast-forward to test theories about dark energy, black hole growth, or the formation of the first stars. But here's the real magic. These simulations are getting so detailed they can spotlight anomalies in our own observations. When astronomers found galaxies rotating faster than expected, simulations helped pinpoint the culprit at dark matter's gravitational grip. When the Hubble constant dispute erupted, supercomputer models revealed how cosmic voids might be skewing our measurements. They've even recreated the cosmic web's filamentary structure, showing how dark matter's invisible scaffolding guides galaxies into their positions like beads on a string. The process is part art, part science. Researchers start with the laws of physics, general relativity, fluid dynamics, quantum mechanics, and sprinkle in initial conditions based on the cosmic microwave background. Then they hit go, watching as virtual universes unfold in accelerated time. Some collapse into chaos, others mirror our own reality eerily well. The goal isn't perfection, it's insight. By tweaking variables, what if dark matter interacts with itself? What if gravity weakens over vast distances? Scientists can explore alternate cosmic histories, testing which scenarios align with the universe we inhabit. Of course, even the most powerful simulations have limits. They can't yet capture the frenzied physics near a black hole's event horizon or the quantum fluctuations of the early universe. But with each leap in computing power, they edge closer. Projects like CAMEL's cosmology and astrophysics with Machine e-learning simulations are now training AI to fill in the gaps, generating ultra-high-resolution snapshots of cosmic dawn or the dance of colliding galaxy clusters. What's truly revolutionary is how these digital universes are changing the way we explore. Instead of blindly scanning the skies, astronomers use simulations as treasure maps, zeroing in on regions where strange phenomena like primordial black holes or wandering supernova are most likely to appear. They're not just simulating the universe, they're using it to write the ultimate guidebook for cosmic exploration, one line of code at a time. We're standing on the brink of a cosmic revolution, one where the maps we make won't just chart stars and galaxies, but decode the very architecture of spacetime itself. The Vera Rubin Observatory, poised to begin its 10-year legacy survey of space and time, will capture the entire southern sky every few nights with a 3.2 gigapixel camera, spotting objects 100 million times fainter than the human eye can see. Imagine a time lapse of the universe at unprecedented scale, where subtle changes, a star flickering before going supernova, a distant quasar flaring, or an asteroid tumbling through our solar system are recorded in a vast, living atlas updated nightly. This isn't just more data, it's a paradigm shift revealing celestial motions and transformations across timescales from hours to decades. But raw observations are only half the story. The flood of data, an estimated 20 terabytes every night, would overwhelm traditional analysis. That's where artificial intelligence steps in, not as a tool but as a collaborator. Machine learning algorithms trained on known phenomena will flag anomalies, perhaps a star dimming in unexpected ways, hinting at a hidden black hole's gravitational lensing. Other AI might spot faint gravitational wave counterparts in visible light, or identify the infrared signatures of rogue planets drifting between stars. The most exciting discoveries won't be the ones we're looking for, but the patterns no human thought to search for, like an AI noticing that certain galaxies cluster in ways that defy dark matter models, or that cosmic voids expand faster at specific angles. This synergy of human curiosity and machine perception will redefine what's possible. Projects like the Square Kilometre Array, with its thousands of radio antennas spanning continents, will map hydrogen gas across the universe in 3 dimensions, the fuel for future stars. The Nancy Grace Roman Space Telescope will combine Hubble's sharp vision with a field of view 100 times wider, capturing the delicate distortions of spacetime around dark matter filaments. Together, these instruments won't just add detail to our maps, they'll expose hidden layers of reality, like switching from a paper roadmap to an interactive model buzzing with real-time traffic, weather, and construction updates. The implications stretch far beyond astronomy. As we trace the universe's large-scale flows with precision, we might finally solve the Hubble tension, or discover it's not an error but evidence of new physics. Mapping the cosmic web's filaments could reveal why galaxies spin faster than expected, or if dark matter interacts with itself. Even the search for extraterrestrial intelligence could get a boost as AI sifts through millions of star systems for technosignatures too subtle for human analysts to catch. What's most thrilling is how little we know about what we'll find. Every leap in observational power has rewritten cosmic understanding, from Hubble proving galaxies exist beyond the Milky Way to Webb spotting impossibly early galaxies that challenge formation theories. The next decade won't just fill in blank spots on our maps. It will remind us that the universe is stranger, more dynamic, and more wonderfully mysterious than our boldest theories dared to suggest. And that's the true promise of this golden age, not just seeing farther, but seeing differently, with fresh eyes that notice what we've been missing all along. Beyond the edge of our cosmic vision lies a mystery so profound it defies comprehension: the unobservable universe. Light from these regions hasn't had time to reach us since the Big Bang, placing them forever outside our view, like islands drifting beyond the horizon. But here's the twist: the universe we can see, a sphere roughly 93 billion light-years across, might be just a speck in something far grander. If the cosmos is infinite, as some theories suggest, then what we call the observable universe is less than a grain of sand on an endless beach. The challenge isn't just distance, it's the very nature of space-time itself. As the universe expands, distant galaxies are carried away faster than light can bridge the gap, their light fading into oblivion like signals from a receding ship. Even if we could travel at light speed, we'd never catch them. This cosmic event horizon means parts of the universe are eternally lost to us, their stories written in photons we'll never receive. Yet theoretical physics offers tantalizing glimpses beyond the veil. Some models propose that other universes, endless variations of our own, might exist in a vast multiverse, each with different physical laws. Others suggest space-time could curve back on itself in higher dimensions, making the edge of our observable universe an illusion, like a two-dimensional creature unaware of the third dimension. Mapping the unmappable requires rethinking what a map even is. Without light to guide us, astronomers turn to indirect clues, like gravitational echoes from the Big Bang or anomalies in the cosmic microwave background that might hint at structures beyond our view. Imagine trying to reconstruct a city's skyline by studying the shadows it casts on fog. That's the scale of inference needed to ponder what lies past the cosmic horizon. Some theorists even speculate that quantum entanglement, the bizarre link between particles across vast distances, could offer a backdoor to understanding these hidden realms, though the idea remains fiercely debated. The most humbling realization: we might be forever stranded on our little island of visibility, surrounded by an ocean of unreachable wonders, but that's also what makes cosmology so thrilling. Every limit we encounter isn't just a barrier, it's an invitation to imagine, to theorize, to push the boundaries of what we think we know. And who's to say that future breakthroughs, whether in quantum physics, higher dimensional math, or technologies we can't yet conceive, won't one day illuminate the darkness beyond? Until then, the ultimate cartographic challenge remains: how do you draw a map of the unknowable? The answer, it seems, is written in the spaces between our theories and our dreams. Black holes don't just bend light, they swallow it whole, leaving behind a perfect silhouette against the glow of superheated gas. That's what made the Event Horizon Telescope's first image of a black hole's shadow so revolutionary. It wasn't just a blurry snapshot of a cosmic monster. It was a direct glimpse at the point of no return, where gravity becomes so strong that not even light can escape. The target, M87, a supermassive black hole 55 million light-years away, with a shadow so vast it could engulf our entire solar system. To capture it, scientists synchronized radio telescopes across the globe, creating a virtual dish the size of Earth itself. The result, a fiery ring of light encircling darkness, a perfect match for Einstein's predictions over a century ago. But that iconic image was just the beginning. Future upgrades aim to sharpen the view, adding more telescopes to the network and even launching space-based receivers to eliminate atmospheric interference. Imagine seeing the black hole's shadow not as a static photo, but as a movie, watching how it flickers as it devours matter, or how its silhouette wobbles as it spins. These details could reveal the true nature of space-time around these gravitational giants. Does it twist exactly as relativity predicts, or are there subtle deviations hinting at new physics? Some theories suggest that black holes might have tiny irregularities in their gravitational fields that betray hidden quantum effects. Others propose that their shadows could flicker in ways that expose the presence of wormholes or exotic matter. What's even more astonishing is how these images are made. The data collected by the Event Horizon Telescope is so vast it can't be sent over the internet. Hard drives filled with observations must be physically flown to supercomputers for processing. Their algorithms stitch together fragments of radio waves into a coherent picture, like reconstructing a symphony from scattered notes. It's a painstaking process, but the payoff is worth it. Each new image doesn't just confirm what we know, it challenges our assumptions. For instance, the black hole in our own galaxy, Sagittarius A star, turned out to be quieter than expected, its shadow flickering less violently than models predicted. Why? The answer might lie in how its magnetic fields channel incoming matter, or perhaps in unseen turbulence in the surrounding gas. These portraits of darkness are more than scientific curiosities. They're testaments to human ingenuity, proving that even the most elusive cosmic phenomena can be pinned down with enough creativity and collaboration. And as the next generation of telescopes comes online, we're not just aiming for sharper images, we're peering deeper into the heart of gravitational madness, where the known laws of physics break down. What waits there might rewrite our understanding of reality itself. Time isn't just something we measure, it's a thread woven into the very fabric of the cosmos, a dimension as real as the three we navigate every day. Imagine holding a map that doesn't just show where galaxies are, but when they were, a cosmic time machine where every point of light comes with a timestamp revealing its history. This is the frontier of space-time cartography, where astronomers aren't just plotting locations but tracing the evolution of the universe itself. Take the Hubble Deep Field, that iconic image capturing thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. At first glance, it's a stunning snapshot, but look closer and it becomes a time lapse. The faintest smudges aren't just far away, they're relics from over 13 billion years ago, their light only now reaching us after an epic journey across the expanding universe. Meanwhile, the brighter, more structured galaxies are comparatively closer and younger, showing us how cosmic architecture has matured over eons. Stack enough of these observations together, and suddenly you're not just looking at space. You're watching it grow up. The real breakthrough comes when we stitch these moments into a continuous narrative. Projects like the Sloan Digital Sky Survey have compiled 3D atlases showing not only where galaxies are today, but how they've moved and interacted over billions of years. It's like finding an old family photo album where the portraits gradually come to life, revealing ancestors you never knew existed. These maps expose cosmic growth spurts, periods when galaxies collided in violent mergers, or epochs when quasars lit up like beacons, their black holes feasting on surrounding gas. But space-time cartography isn't just about looking back. By simulating the universe's expansion, scientists can project forward, forecasting celestial events with uncanny accuracy. We know, for instance, that the Milky Way and Andromeda will collide in about 4 billion years, their spiral arms tangling into a new elliptical galaxy. These predictions aren't guesses, they're extensions of the same physics that let us reconstruct the past, proving that time's arrow cuts both ways in our cosmic maps. The most mind-bending application, gravitational wave astronomy. When two black holes merge, they send ripples through space-time that detectors like LIGO can pick up. But those waves don't just tell us where the collision happened. They encode when it occurred, even if the event was billions of years ago. It's as if the universe keeps its own ledger of violent encounters, and we're just learning to read the entries. What's thrilling is how this changes our relationship with the cosmos. A static map implies a finished story, but a space-time atlas reveals an epic still being written, one where we're not just observers but participants. Every new observation, every refined simulation adds another frame to the movie, and as our tools grow sharper, we're not just charting the universe's history. We're learning to predict its destiny. Cosmic archaeology doesn't require shovels or brushes, just telescopes powerful enough to peel back the layers of time. Every ancient star we observe is a relic, a time capsule preserving the chemical fingerprints of the early universe. Take HD 14283, a star so old it formed when the cosmos was barely a billion years young. Its atmosphere holds barely any heavy elements, just traces of hydrogen, helium, and lithium, proof it was born from the primordial gas that filled the universe before generations of supernova enriched it with metals. Studying stars like this is like finding a cave painting untouched for millennia, offering a raw, unfiltered glimpse into the cosmos's infancy. But stars aren't the only fossils out there. Scattered across the galactic outskirts are ultra-faint dwarf galaxies, surviving remnants of the universe's first building blocks. These ghostly collections of stars, like Segway 1 or Boots 1, contain only a few thousand suns, but their importance is colossal. Their motions betray the gravitational pull of dark matter, while their simple chemistry reveals how the first galaxies assembled in the chaos of the early cosmos. Some may even be the mangled cores of once larger galaxies, shredded by collisions and stripped down to their barest skeletons over billions of years. The real detective work begins when we piece these clues together. By measuring the ratios of elements in ancient stars, astronomers reconstruct the lives and deaths of the very first supernova explosions so powerful they seeded the universe with carbon, oxygen, and iron. These chemical autopsies reveal that the earliest stars weren't like the ones we see today. They were giants, hundreds of times more massive than our sun, burning furiously and dying young in spectacular blasts that lit up the darkness. Their ashes became the raw material for everything that followed: planets, life, even us. Then there are the cosmic ghosts, structures like the Gaia sausage, the mangled remains of a dwarf galaxy that collided with the Milky Way 8 to 10 billion years ago. Its stars orbit backward, a telltale sign of a long-ago merger that reshaped our galaxy forever. Similar scars litter the Andromeda Galaxy, evidence of its own violent past. These galactic fossils remind us that the universe isn't static. It's a graveyard of collisions, mergers, and rebirths, each event leaving behind traces we're only now learning to read. The most astonishing part, this excavation is far from over. New telescopes like the James Webb Space Probe are spotting galaxies so distant, and therefore so young, that they shouldn't exist under current theories. Others are uncovering stars with bizarre chemical signatures, hinting at entirely unknown types of supernova or even exotic forms of dark matter. Every discovery adds another brushstroke to the portrait of cosmic history, proving that the past isn't lost, it's written in the sky, waiting for us to decipher it. Imagine sifting through a mountain of sand, searching for a single unique grain, except the mountain is as tall as Everest, and you have only seconds to find it. That's the challenge astronomers face with modern sky surveys, where telescopes capture petabytes of data every night. Enter artificial intelligence, the silent revolution transforming how we map the cosmos. These algorithms don't just crunch numbers, they spot patterns invisible to human eyes, uncovering celestial oddities and cosmic connections buried in the noise. Take the case of galaxy classification. For decades, astronomers painstakingly sorted spiral galaxies from ellipticals by hand, a process as slow as it was subjective. Now, neural networks trained on millions of labeled images can categorize galaxies in milliseconds, with accuracy surpassing human experts. But AI's real power lies in its ability to spot the unexpected. In 2018, a machine learning model scanning data from the Kepler Space Telescope flagged a bizarre dimming pattern around a distant star, a signature that led to the discovery of Boyajian star, an object with such erratic light fluctuations that some speculated wrongly it turned out about alien megastructures. No human had noticed the anomaly, lost as it was in terabytes of mundane data. The magic happens in the way these algorithms learn. Unlike traditional software, which follows rigid rules, AI adapts. Feed it enough examples of supernova, and it'll recognize the telltale brightening of a dying star even in low-quality images. Show it gravitational lensing arcs, and it'll pinpoint warped galaxies hiding in telescope snapshots. Some systems, like Google's DeepMind, have even taught themselves to predict the motions of stars in globular clusters, solving complex n-body physics problems faster than conventional simulations. Perhaps most astonishing is how AI handles the universe's biggest mysteries. When researchers at the University of Heidelberg trained a model on dark matter simulations, it learned to reconstruct the invisible cosmic web from the distribution of galaxies alone, a task that would take supercomputers weeks, done in seconds. Other teams use AI to hunt for gravitational wave signals in LIGO data, teasing out faint chirps from black hole mergers that standard methods might miss. There's even an algorithm designed to predict solar flares by analyzing the sun's magnetic field patterns, potentially giving astronauts and satellites life-saving warnings. Yet for all its brilliance, AI isn't replacing astronomers, it's amplifying them. Tools like AstroNet, developed by NASA, act as tireless assistants, pre-screening telescope data to highlight the most promising targets for human follow-up. Citizen science projects harness machine learning too, guiding volunteers to classify unusual objects in platforms like Galaxy Zoo. The result, discoveries that once took years now unfold in real time, from rogue planets drifting between stars to quasars flickering in ways that challenge black hole theories. The future is even wilder. Imagine AI-controlled telescopes that autonomously decide which cosmic events to observe, prioritizing rare supernova or asteroid close approaches without human input. Or algorithms that design entirely new observational strategies, optimizing telescope time to answer questions we haven't even thought to ask. Already, AI is helping plan the routes of Mars rovers and the observation schedules of the James Webb Space Telescope, tasks too complex for manual scheduling. What's clear is that we're not just mapping the cosmos anymore. We're teaching machines to explore alongside us, turning the endless deluge of data into a goldmine of discovery. And as these systems grow more sophisticated, they're not just finding answers, they're helping us ask better questions about the universe we call home. The moment we reach beyond our solar system, we step into an ethical frontier as vast as space itself. Mapping distant worlds isn't just a technical challenge, it's a moral one. Consider the possibility of discovering a planet teeming with microbial life in the clouds of Proxima Centauri b. Do we have the right to land probes that might contaminate its atmosphere? Or take the hypothetical scenario of finding an abandoned alien megastructure. Would studying it be archaeology or grave robbing? These aren't science fiction scenarios anymore. With breakthroughs like the James Webb Telescope analyzing exoplanet atmospheres and projects like Breakthrough Starshot planning interstellar probes, we're on the cusp of making these dilemmas real. History offers sobering lessons about exploration without ethics. When European ships reached untouched islands, they often brought invasive species, diseases, and cultural destruction alongside scientific discovery. Space exploration risks repeating these mistakes on a cosmic scale, except this time, we might be the invasive species. The dust storms of Mars could carry Earth microbes to delicate environments, while our radio signals might unintentionally announce our presence to civilizations unprepared for contact. Even seemingly benign acts like mining asteroids for rare minerals could destabilize fragile orbital systems that took billions of years to form. Yet the opposite extreme, never venturing beyond Earth, carries its own ethical weight. By staying silent, we might miss warning signs of existential threats like rogue asteroids or gamma-ray bursts. And if life exists out there, don't we have a responsibility to understand it? The Viking landers carried experiments specifically designed to detect Martian metabolism, not just chemistry, a recognition that life deserves more than passive observation. Some argue that intelligence brings an obligation to explore, to share knowledge across the stars, just as indigenous navigators once connected island cultures across vast oceans. The solution may lie in frameworks like the Outer Space Treaty, which prohibits nuclear weapons in space and declares celestial bodies the province of all mankind. But these 20th century rules weren't written for an era of private space companies and AI explorers. New guidelines are emerging like NASA, planetary protection protocols that sterilize Mars rovers, or the METI messaging extraterrestrial intelligence debates about whether we should actively signal our presence. Perhaps what's needed is a cosmic version of the Prime Directive from Star Trek, adapted for real-world complexities. What makes this challenge unique is the timescale. Unlike colonial expeditions that played out over years, interstellar consequences might take centuries to manifest. A probe sent today could reach another star system long after our civilization has forgotten it launched. That's why ethicists suggest building time capsules of responsibility into our spacecraft instructions in universal languages explaining our peaceful intentions, warnings about biological hazards we might carry, even apologies for unintended harms. At its heart, this isn't just about avoiding mistakes. It's about deciding what kind of galactic species we want to be. Will we be the careful archivists of cosmic wonders or the bulldozers of the final frontier? The stars won't judge us, but our descendants and perhaps other civilizations certainly will. And that judgment may rest on the choices we make in these crucial early years of interstellar cartography, when every new map we draw comes with the power to preserve or disrupt realms we're only beginning to understand. Our journey through interstellar cartography doesn't just fill in blank spots on a map. It rewrites what we thought we knew about reality itself. Those swirling galaxies we once saw as isolated islands are now understood as knots in a vast cosmic web, connected by invisible threads of dark matter. The empty voids between them aren't really empty at all, but thrumming with quantum potential and magnetic fields we're only beginning to detect. Even the black holes we feared as cosmic dead ends have become laboratories, bending space-time in ways that reveal the universe's deepest rules. Every time we think we've grasped the full picture, the cosmos shows us how much we've missed. Take dark energy. What started as a puzzling mismatch in cosmic expansion rates has blossomed into one of physics' greatest mysteries, suggesting that 70% of the universe's energy might be woven into the fabric of space itself. Or consider fast radio bursts, those millisecond flashes from distant galaxies that defy explanation. Are they collapsing neutron stars, alien signals? Or something we haven't even imagined? The beauty lies in the questions, not just the answers. What's thrilling isn't merely the scale of our discoveries, but how they transform our place in the story. We've gone from believing Earth was the center of creation to realizing we're specks on a speck, orbiting an average star in the quiet suburbs of an unremarkable galaxy. Yet this humility unlocks something extraordinary, the realization that the same laws governing quasar jets and colliding galaxy clusters also shape the neurons firing in your brain as you ponder them. We're not just observers of the cosmos, we're its way of understanding itself. The tools we're building today would seem like magic to past generations. Telescopes that can weigh planets light years away by the wobble of their stars. Detectors that feel the tremors of black holes merging billions of years ago. Simulations that recreate the universe's first seconds with quantum precision. But the most powerful instrument remains human curiosity, that relentless drive to look beyond the next horizon, whether it's the icy plains of Pluto or the event horizon of a supermassive black hole. As we stand on this threshold, it's clear that interstellar cartography is more than science. It's a testament to our species' boundless imagination. Those ancient star maps carved in mammoth tusks 12,000 years ago, they were the first tentative strokes in a masterpiece we're still painting. And while we'll never complete the work, the universe ensures there's always another layer to uncover. That's precisely what makes the endeavor so glorious. The map isn't the territory, and the cosmos will always outpace our attempts to chart it. But in trying, we touch something eternal, the wonder of a universe that invites us to keep exploring, one starlit question at a time. If this journey through the unseen corners of the cosmos has left you awestruck, you're not alone. The universe is full of mysteries waiting to be uncovered, and this is just the beginning. To keep exploring the farthest reaches of space with us, hit that like button and subscribe. It's your ticket to more mind-bending discoveries, from the enigmas of dark matter to the wild frontiers of exoplanet hunting. But we want to hear from you too. Drop a comment below and tell us which cosmic wonder captivates you the most. Is it the ghostly pull of the Great Attractor? The eerie silence behind the Fermi Paradox? Or maybe those rogue planets drifting like cosmic nomads through the void? Your curiosity fuels this adventure as much as the science does. And remember, every time you gaze up at the night sky, you're looking at a story still being written. The next breakthrough could be just a telescope's glance away. Until our next cosmic deep dive, stay curious, stay wondering, and most of all, keep reaching for the stars.